All right, let's dive deep into the universe. We're going to explore how we humans figured out what this whole vast cosmos is all about.
Yeah, from those early ideas, folks had to, the really mind-blowing discoveries in modern physics.
Exactly. And, you provided the perfect guide to get us through all this.
Oh, yeah.
Yeah, an excerpt from Stephen Hawking's book, The Theory of Everything.
Oh, fantastic choice.
Yeah, it's a collection of 7 lectures, so it's really like a crash course on cosmology from, one of the most brilliant minds, ever. And we're going to be talking about those early conceptions of the universe and then diving deep into black holes and then even exploring the possibility of a unified theory of everything.
That's right, covering a lot of ground.
Yeah, so we're going to start thousands of years in the past, long before telescopes and spaceships.
Right.
And you might be surprised to learn that Aristotle, all the way back in 340 BC,
wow,
already has some pretty solid arguments for why the Earth is a sphere.
Yeah, that's right. Aristotle, we think of him as a philosopher, but he was making some really astute observations about the natural world, too.
So just by observing the world around him, he made some keen deductions like
during a lunar eclipse, for instance.
No.
The Earth's shadow on the moon is always round, right?
Right.
And if the Earth were flat, you'd expect that shadow to be distorted, wouldn't you?
Yeah, that's true. I never thought about it that way.
And he also noticed that as you travel south, the pole star appears lower in the sky. And there's also that classic observation about ships sailing towards you. They seem to emerge from the horizon sails first.
Right.
All of these kind of point towards a curved surface, right? A sphere.
So even back then, people were piecing together these clues about the nature of our world.
That's right.
But Aristotle wasn't totally right, was he?
Well, he was right about the Earth being a sphere.
Right.
But
he still believed in that geocentric model with the Earth at the center of everything.
Yeah, that idea of a central stationary Earth, it really fit with the prevailing worldview at the time, both philosophically and religiously. And this model, it was further elaborated upon by Ptolemy centuries later with his system of spheres.
Right. And so even that sophisticated model had problems.
Oh, it did.
Didn't they have something like, I think it was with the moon changing size in the sky or something?
Yes, exactly.
Yeah.
Ptolemy's model required the moon to drastically change size to match observations.
Right.
Which, of course, we know doesn't happen.
Right.
But it's interesting how a model can persist for centuries, even with obvious flaws, if it fits, the accepted narrative.
It really makes you think about how we cling to assumptions sometimes.
It does indeed. But luckily, science is about challenging those assumptions, right?
Right.
Refining our understanding. And a major shift came in the 16th century with Copernicus.
Copernicus. He's the one who dared to propose that the sun, not the Earth, was at the center of it all.
A true revolutionary.
Yeah.
And it wasn't without risk. Copernicus actually delayed publishing his model for years. Yeah. Oh, yeah. He feared backlash from the church. He knew it challenged the established order.
But eventually, his ideas, combined with Galileo's telescope observations a century later, really helped pave the way for a new understanding of our solar system.
Yeah, Galileo's observations of Jupiter's moons were particularly crucial, you see. They showed that not everything orbited the Earth directly.
Oh, okay.
It provided strong evidence for that heliocentric model.
So, okay, we've got the sun at the center.
Yeah.
But even with that in place, the orbits that were predicted by Copernicus and Galileo didn't perfectly match the actual paths of the planets, right?
You're right, and it was Kepler who kind of cracked the code there. He realized that planets move in ellipses.
Oh.
Not perfect circles.
Interesting.
And that seemingly small adjustment brought the model into alignment with observations.
That's incredible. It shows how sometimes letting go of a cherished idea,
like a perfect circles, can lead to a major breakthrough.
Even then, we're still missing a crucial piece of the puzzle. What keeps these objects in orbit in the first place?
That is the question, isn't it? And that's where Sir Isaac Newton comes in.
Right.
With his law of universal gravitation.
Yeah.
It was a revolutionary concept that explained not just the orbits of planets, but also something we experience every day here on Earth.
What's that?
Why things fall down.
Hold on. Are you saying that the same force that keeps the planets in orbit around the sun is responsible for an apple falling from a tree?
That is exactly what I am saying.
That's mind-blowing.
It's all about this force of attraction between any two objects with mass.
Okay.
A force that depends on their masses and the distance between them.
So the bigger the mass is, the stronger the pull.
Exactly. And the closer they are, the stronger the force as well.
So Newton's law was a game changer. It unified all these seemingly disparate phenomena.
It did.
And it explains why objects behave the way they do.
Both on Earth and in the heavens.
Yeah, but there were still puzzles to solve.
No, there always are.
For instance, Newton's law implied a dynamic universe. But most scientists at the time were still fixated on the idea of a static, unchanging cosmos.
Right, clinging to those old ideas.
And that is where things start to get really, really big. Because we're not just talking about our solar system anymore.
Right.
We're talking about galaxies.
Galaxies, those vast islands of stars.
Right. And in the early 20th century,
astronomers started to really explore those distant realms.
Yeah, Edwin Hubble made a series of groundbreaking discoveries.
Using really clever methods to measure these vast distances to stars,
Right.
he proved the existence of galaxies beyond our own Milky Way.
So our galaxy, with its billions of stars, is just one amongst billions of others.
Isn't that amazing?
It's hard to even grasp. It makes you feel pretty insignificant.
It does put things into perspective, doesn't it?
It does. It really does. But Hubble's discoveries, they didn't stop there.
Oh, no.
In 1929, he dropped another bombshell.
Another one.
The universe is expanding.
That's right.
He observed that distant galaxies were moving away from us, and the farther away they were,
the faster they were receding.
So the universe isn't static.
Nope.
It's constantly growing.
The universe is in motion.
So Hubble's observations were based on something called redshift.
Yeah. Have you ever heard of the Doppler effect?
Yes. Like with a passing car's engine.
Exactly.
Yeah.
So as the car approaches, the sound waves are compressed and the pitch sounds higher.
Right.
And as it moves away, the waves stretch out, the pitch gets lower.
Yeah.
Light waves behave similarly. And Hubble noticed that light waves from distant galaxies were shifted towards the red end of the spectrum, indicating they were moving away from us.
That's incredible. But hold on. If everything is moving away from us, doesn't that mean we're at the center of the universe?
Mm-hmm. It's a natural thought, but not quite right.
Okay.
Think of it like baking raisins into a loaf of bread.
Okay.
As the bread rises, all the raisins move farther apart.
Mm.
But no single raisin is the center of the expansion.
I see.
Same with galaxies in the universe.
So it's space itself that's expanding.
That's the key insight. It's space itself that's stretching, carrying the galaxies along with it.
That makes sense.
Good.
Okay, but if the universe is expanding, does that mean it had a beginning?
That's a very profound question.
Some point where it was all packed together.
That brings us to the concept of the Big Bang.
Right.
Which we'll delve into more next time. But before we get there,
okay,
let's go back a bit further in time before Hubble.
All right.
To a Russian physicist named Alexander Friedmann.
Friedmann? What was his contribution to all of this?
He was way ahead of his time.
Yeah.
Based on Einstein's theory of general relativity, Friedmann developed models that predicted an expanding universe.
Wow.
Even before Hubble's observations.
So he just figured it out.
He did, and he did so by making two key assumptions about the universe.
What were those?
First, he assumed that on a large scale, the universe looks the same in every direction.
Okay.
And second, that this uniformity holds true from any point in the universe.
So no matter where you are in the cosmos, it would look roughly the same.
You got it, no preferred location.
That's a bold assumption.
It is, but it's consistent with what we observe.
Mm-hmm.
And based on these assumptions and Einstein's equations, Friedmann derived these models of an expanding universe, remarkably similar to what Hubble would later observe.
That's pretty incredible.
It is, isn't it?
So Friedmann's models, fueled by general relativity, predicted this expanding universe.
They did.
But what did those models say about the beginning of the universe?
That brings us to the mind-boggling concept of the Big Bang, which we will delve into next time, along with one of the most intriguing consequences of general relativity, the existence of black holes.
Black holes, those cosmic enigmas that warp space and time.
The very same.
I can't wait to dive into those. Stay tuned, listeners, because next time things are going to get even weirder.
Just getting started. Welcome back to our deep dive into the universe. Last time we left off with that tantalizing idea of the Big Bang.
Right, this mind-boggling concept that the entire universe was once packed into an incredibly dense and hot state.
It really is hard to wrap your head around it.
It is everything we see around us, all the galaxies, stars, planets, even us originating from a single point.
It's a pretty profound idea, and it emerges naturally from the observation that the universe is expanding.
So if we rewind that expansion like a film running in reverse,
everything converges towards a single point.
But what caused this Big Bang? What set the universe on this path of expansion?
That's where our current understanding of physics hits a wall. The Big Bang represents a singularity. A point where the density and temperature of the universe were infinite.
Right.
Where our current laws of physics just break down.
So we need a new theory, something beyond general relativity and quantum mechanics, to truly grasp the Big Bang.
Exactly. We need a theory of quantum gravity.
Okay.
A framework that can reconcile the smooth, continuous nature of space-time and general relativity with the grainy, quantized world of quantum mechanics.
And the search for this theory is one of the most challenging and exciting frontiers in modern physics.
It really is a holy grail for physicists.
So how do we even begin to look for such a theory? Where do we start?
One approach is to kind of revisit the very foundations of quantum mechanics.
Okay.
And specifically an idea called Feynman's sum over histories.
Feynman's sum over histories. That sounds intimidating.
It might sound complex, but the basic idea is actually quite intuitive.
Okay.
Imagine you're driving to work.
Okay.
In the classical world, you take one specific route, right?
Yeah, of course, unless there's traffic.
Right. But in the quantum world, Feynman proposed that a particle like an electron doesn't just take one path.
Okay.
It explores every possible path simultaneously.
Wait, so the electron is somehow taking every possible route to work at the same time?
That's the essence of it.
That's wild.
Each path has what's called a probability amplitude, which is kind of like a wave. And to get the probability of the electron actually arriving at its destination, you have to add up the contributions from all these waves,
right,
taking into account their amplitudes and their phases.
It's like a cosmic interference pattern.
Exactly.
With all these electron waves overlapping and interacting.
You got the sum over histories considers all possible paths and their interferences to figure out the final probability of the electron's behavior.
Okay, so that's how it works for particles.
Right.
But we're talking about quantum gravity, the entire universe.
Yeah.
How does this sum over histories idea apply on such a grand scale?
Here's where things get really mind-blowing.
Okay, let's hear it.
Instead of summing over the histories of particles, we sum over the histories of the entire universe.
So we're imagining different possible universes, each with its own history, and somehow combining them all.
That's the general idea.
Wow.
A history of the universe in this framework is like a complete space-time, representing its evolution from beginning to end. And we imagine the universe exploring all these possible space-times, just like a particle explores all its possible paths.
So we're treating the entire universe as this giant quantum object.
Precisely.
Subject to these bizarre quantum rules.
That's the idea, but there's a catch.
What's that?
When you try to do the sum over histories for gravity, things get really mathematically difficult. The equations become incredibly complex and just hard to handle.
So how do we deal with that mathematical mess?
Well, the only way to make progress is to introduce a rather strained concept.
What is it?
Imaginary time.
Imaginary time? Is that like something out of Alice in Wonderland?
It might sound fantastical, but it's a well-defined mathematical tool.
Okay.
Instead of thinking of time as this linear progression, we imagine it having this imaginary component. And when we do that, something remarkable happens.
What happens? Does time start flowing backwards?
Not quite. What happens is the distinction between space and time kind of blurs. Space-time, instead of being dynamic and ever-changing, becomes more like a static geometrical object.
So imaginary time turns the universe into a frozen snapshot.
That's a good way to visualize it. And in this frozen picture, the sum over histories becomes much easier to handle mathematically.
Okay, so we're working with imaginary time summing over these possible universe histories. But how do we decide which of these histories is the most likely? Don't we need some kind of starting point for the universe?
That's where Stephen Hawking and his collaborator James Hartle made a very bold proposal.
Okay.
The no-boundary proposal.
No boundary. What does that mean?
Think of the surface of a sphere.
Okay.
It's finite in size.
Right.
But it has no edges, no boundaries.
I see.
Hawking and Hartle suggested that space-time in imaginary time is similar. It's finite, but without boundaries.
So no Big Bang singularity?
Not in the usual sense.
No beginning or end of time?
In imaginary time, the no-boundary proposal essentially says that the universe is self-contained, boundless. It exists without the need for a specific starting point.
Okay, so where does that leave us with the Big Bang? Does it still happen?
When we translate this picture back to real time, the Big Bang still appears as a special moment in the universe's history.
Okay.
But it's no longer a singularity where everything breaks down.
So the Big Bang is more like a transition.
Yeah.
A smooth emergence from this boundless state, rather than an explosion from a single point.
That's one way to think about it. The no-boundary proposal helps to smooth out the Big Bang,
Right.
making it less problematic from a mathematical and conceptual standpoint.
That's pretty neat. So the no-boundary proposal helps us understand the very beginning of the universe,
Yeah.
but what does it say about the universe's evolution after the Big Bang?
Well, the no-boundary proposal combined with that sum over histories actually leads to some remarkable predictions.
Oh, yeah.
It suggests that the early universe would have undergone a period of incredibly rapid expansion.
Inflation.
Exactly.
I've heard about that. Wasn't that a brief period where the universe expanded exponentially faster than the speed of light?
That's right. And the no-boundary proposal provides a natural explanation for why inflation would happen. It's as if the universe, exploring all these possible space-times,
Yeah.
found that inflationary path to be the most probable one.
So inflation isn't just an add-on to the Big Bang model.
Right.
It's a natural consequence of this deeper quantum gravity framework.
That's the power of this approach. And inflation, in turn, helps explain many features of the universe we observe today.
Like what?
Like its large-scale uniformity and the seeds of structure that eventually gave rise to galaxies and stars.
So quantum gravity, via this strange journey through imaginary time and boundless universes, helps us understand not just the beginning of the universe, but also its subsequent evolution.
That's the beauty of it, connecting the microcosm of quantum mechanics with the macrocosm of cosmology.
Offering a tantalizing glimpse of a unified theory.
Exactly.
But we're still searching for a complete theory of quantum gravity, right?
Oh, absolutely.
The no-boundary proposal is just one piece of the puzzle.
It provides a framework, but there's still much work to be done.
Right.
And one of the most prominent approaches to kind of tackling this challenge is string theory.
Ah, string theory, the idea that everything is made of these tiny vibrating strings.
That's the basic concept.
Yeah.
String theory attempts to unify all the fundamental forces of nature, including gravity, by describing them as different vibrations of these fundamental strings. It's a really elegant and ambitious idea.
So instead of particles like electrons and quarks, we have these tiny strings as the fundamental building blocks of everything.
Exactly. And this seemingly simple shift has some really profound implications.
Like what?
For example, string theory requires extra spatial dimensions.
Oh.
Beyond the three, we experience up, down, left, right, forward, backward.
Extra dimensions, like something out of science fiction.
It might sound strange, but it's a mathematical necessity in string theory.
Okay.
These extra dimensions are thought to be curled up or compactified into extremely small sizes, far too small for us to detect directly.
So we're like ants crawling on a thin sheet of paper.
A good analogy.
Unaware of this vastness of the three-dimensional world surrounding us.
String theory suggests that our perception of reality is limited by the scale at which we can observe it.
That's mind-blowing.
Yeah.
So string theory offers this potential route to unifying gravity with the other forces.
It does.
But it also brings with it these extra dimensions,
Right.
which are both intriguing and perplexing.
Indeed, string theory is a very complex framework.
Yeah.
And there are still many challenges and open questions.
I see.
But it offers this glimpse of a universe far richer and stranger than we might have imagined.
So we've gone from the sum over histories to the no-boundary proposal, and now we're venturing into the realm of string theory and extra dimensions. It feels like we're pushing the very limits of human understanding.
The quest for a unified theory is a journey into the unknown, driven by this deep desire to understand the fundamental nature of reality.
Right.
And it's a journey that Stephen Hawking was deeply involved in throughout his career.
It is incredible to think that he played such a pivotal role in shaping our understanding of the universe. And as we continue this deep dive in Part 3, we'll explore some of the implications of these ideas for one of the most fundamental aspects of reality, the nature of time.
Until then, keep those neurons firing.
Welcome back to the final part of our deep dive into the universe. It's been a wild ride so far.
Yeah, from ancient ideas of the cosmos
to the mind-bending realms of black holes and
expanding universes,
quantum gravity, all that stuff. And now for the grand finale, we're going to tackle one of the biggest mysteries of them all time.
Time, yeah. It's something we all experience, but it's so hard to really define.
It is. It feels like it flows, inexorably forward.
Right, it never goes backwards.
Yeah. But is that really how time works at the most fundamental level?
That's the question.
It's such a basic part of our existence.
Yeah.
But when you really start thinking about it, time gets really weird really fast.
It really does. And our intuition about time, much like our intuition about the cosmos, needs some serious revising in light of modern physics. Both general relativity and quantum mechanics have really profound implications for our understanding of time.
Okay, so let's start with general relativity. How does Einstein's theory mess with our everyday notion of time?
Well, general relativity tells us that gravity warps space-time.
Okay.
And this warping doesn't just affect space. It affects time as well.
Interesting.
Time actually slows down near massive objects.
Like in that movie Interstellar, where the astronauts experience time differently near a black hole.
Yeah, that's a good example, though. The movie takes some liberties for sure.
Right, of course.
But the point is, time is not absolute. It's relative.
Okay.
It depends on where you are and the gravitational field you're experiencing.
So time is more like a stretchy fabric than a rigid metronome,
That's a great way to put it, yeah.
speeding up or slowing down depending on gravity.
Exactly. And this relative nature of time, it leads to some really mind-boggling consequences.
Like what?
Well, for example, there's no single now that everyone in the universe agrees on. What's happening right now for you? Might be the past or the future for someone else, depending on their location and their relative motion.
Wait, so you're saying simultaneity is an illusion?
In a sense, yeah.
That there's no universal clock ticking away for everyone?
That's one of the implications of general relativity. What we perceive as now is tied to our specific reference frame, our location in space-time.
So if I could somehow see what's happening right now on a planet millions of light years away,
You'd actually be seeing events that happened millions of years ago in their past because the light from those events took millions of years to reach you.
wow, that's a lot to think about. So
Right.
general relativity tells us that time is warped by gravity
Right.
and that simultaneity is relative.
Yes.
But what about quantum mechanics? How does that shake up our understanding of time?
Quantum mechanics is even weirder in a way. It treats time as an operator, a mathematical entity that acts on the wave function of a system.
Okay.
Remember, the wave function describes the state of a quantum system.
Right, like we were talking about with the sum over histories.
Yeah. Exactly all those possible paths a particle could take.
Yeah.
So in quantum mechanics, time isn't just this passive background. It's an active player that can change the state of a quantum system.
And this leads to some strange effects like quantum entanglement.
Entanglement is a great example. It's this bizarre phenomenon where two particles are linked in a way that just defies our classical intuitions about space and time.
Okay.
You can separate these particles by vast distances, yet they remain correlated.
It's like they're communicating faster than light.
It's not quite like that. Information isn't traveling faster than light. It's more like the entangled particles. They share this single non-local wave function that transcends our usual notions of space and time.
Wow, okay, my brain is officially melting.
It happens.
So both general relativity and quantum mechanics give us these very different views of time that we experience in everyday life.
They do.
And this brings us to one of the most fundamental questions about time.
Which is?
Does it have a direction?
The arrow of time.
Yeah, we perceive time as flowing from past to future.
Right.
But do the laws of physics themselves dictate this direction?
Well, there are different arrows of time. One is the thermodynamic arrow,
Okay.
related to the increase of entropy.
Entropy, that measure of disorder in a system.
Right, things tend to get messier over time.
Like a broken cup doesn't spontaneously reassemble.
Exactly. Or a hot cup of coffee doesn't just get hotter on its own.
Yeah.
Entropy generally increases, and that defines the thermodynamic arrow of time.
But does that mean time itself has a direction? Is that baked into the fundamental laws of physics?
That's a really interesting question. And here's the thing. Most of the fundamental laws of physics are time symmetric. They work equally well whether time is flowing forward or backward. If you could reverse the motions of all the particles in a system, the laws would still hold.
So why do we experience time moving only one way?
It's thought to be a consequence of the initial conditions of the universe, the early universe, right after the Big Bang was in a state of very low entropy.
So the Big Bang was a very tidy affair.
Relatively speaking, yes. And as the universe has evolved and expanded,
Right.
entropy has been increasing, leading to the arrow of time that we perceive.
So the arrow of time isn't built into the laws themselves,
Not really.
but rather it emerges from the universe's starting conditions.
That's the current thinking.
Wow, so the direction of time we experience is a result of the universe's history, not some fundamental law.
That seems to be the case.
And this raises some fascinating questions like, what if the universe stopped expanding and started contracting?
Yeah,
Would time run in reverse? Would we see broken cups reassemble?
that would be something, wouldn't it?
It would, but didn't Stephen Hawking propose that even if the universe were to contract,
He did.
time wouldn't necessarily flow backwards?
Initially, he thought time might reverse in a contracting universe, but based on his work with the no-boundary proposal, he later revised that view. He concluded that entropy would likely continue to increase even in a contracting phase.
So no time travel paradoxes.
At least according to this framework.
It's incredible to think that something as fundamental as time is still shrouded in so much mystery.
It is, but that's part of what makes cosmology so exciting.
It is.
We're constantly pushing the boundaries of knowledge, questioning our assumptions and seeking deeper understanding.
Well, listeners, we've reached the end of our deep dive.
Yeah, time flies when you're exploring the universe.
It really does. We've journeyed from ancient conceptions of the cosmos to the mind-bending world of quantum gravity black holes and the arrow of time.
We've covered a lot of ground.
We have, and Stephen Hawking's The Theory of Everything has been a fantastic guide.
It has been.
Leading us through some of the most profound ideas in physics.
And even though there are still many mysteries left to unravel, the quest for understanding is what drives us forward.
It is. That would be the ultimate triumph of human curiosity and ingenuity.
It would be, wouldn't it?
But even without a final theory, the journey itself is incredibly rewarding.
It is, so keep asking questions, keep exploring, and keep looking up at the stars with a sense of wonder.
That's great advice. And that wraps up our deep dive. Thanks for joining us.